A rock thrown vertically upward from the surface of the moon at a velocity of 24 meters per second reaches a height of, then they give you the function, so that's nice. Right, you'll notice that the gravitational constant has changed. All right, instead of having a leading coefficient of negative 16 if it were in feet or negative 4.9 if it were in meters, it's now negative 0.8 because the value for gravity, the gravitational pull on the moon is much less than here. All right, so write the rock's velocity and acceleration functions or as functions of time. So we have s of t, very easy, already given to us, that's why it's easy. Just rewriting. Velocity, v of t, is s prime of t, so the derivative of my position function. All right, so applying the power rule, derivative of 24t would just become 24. The derivative of negative 0.8t squared, again, multiply power by coefficient, you get negative 0.16, or 1.6. Jeez. T to the first power, so you just leave the t without the exponent there. All right. So power multiplied by coefficient, reduce the power by 1. All right, so that's our velocity function. Our acceleration function, a of t, would be the second derivative of the position function. That's true, but it could also be considered the first derivative of my velocity function. All right, so whatever I got for velocity, I would take the derivative of that again. The derivative of 24 is 0. 24 is constant. Rate of change of something that's constant would be equal to 0. All right, that negative 1.6t, that would become negative 1.6, just negative 1.6, that's it. Because power multiplied by coefficient becomes negative 1.6 t to the 0th power. All right, so that's our acceleration function. And since acceleration is talking about an object that's being thrown downward vertically, or at least in this case, thrown downward vertically on the moon, but the only thing that would be impacting its motion would be the acceleration due to gravity beyond the initial downward force. All right, so acceleration is a steady constant, negative 1.6 meters per second squared. All right, but this is a function, so we don't need the units for that. But what this gives us, I mean, assuming that the function was accurate to begin with, this would be the acceleration due to gravity on the moon. All right, so the second derivative of the position function would give you that. How long did it take the rock to reach its highest point? All right, so you look at the position function graphically, it's going to be a parabola because you see a power of 2. It's going to be a parabola that opens downwards because of the negative leading coefficient. So there will be a high point. All right. Oh, and I said thrown vertically downward. I meant vertically upward because it says it right there. So this object is being thrown upward. It'll reach a high point, and then gravity will pull it back down. So, well, gravity's always pulling it, but it's going to influence it in a downward direction beyond its vertex. So I could do this a couple of different ways. I can just type it into Desmos. That would be one way. Another way, well, we know how to find a vertex for a parabola. All right, that's algebra 1, so you could do that too. But you probably want to go the path of least resistance. So this would be what the graph would look like if it had a terrible window. So let's get a pretty good window. Oops. I'm going to start with a little bit of zoom in first, and then I'll adjust the window value. So it looks like somewhere around the 30 mark. Well, exactly at the 30 mark, it'll be back down on the surface. All right. So, you know, round about 15 seconds, we're looking at it reaching its highest point. But let's confirm that. So I'm going to zoom out, get that highest point, which looks like it's somewhere in the neighborhood of 200. So what I'll do is I'll change my window to go from 0 to 200 for the y, 0 to 30 for the x. Gives a good looking graph there. Now, just getting the answer is one thing. You're expected to provide an analytic solution. All right, so there's going to be some calculus in here. All right, so you think about the object as it's going through the air, or the atmosphere and the moon, whatever that is. It's going to reach a high point of 180 meters after 15 seconds. But how do we get that analytically? How do we get that using the algebra of calculus? Well, the velocity would be at a value of 0 once it reaches its highest point. All right, so it's launched from the surface. It's increasing in height, but its rate of increase is decreasing. Right, so it's slowing down until it gets to its high point, and it settles at a velocity of 0 for just a split second, at which point it starts accelerating in the downward direction. All right. So we just need the instance in which the velocity is equal to 0. All right. So to get the highest point, so for a maximum or a minimum, set your velocity function equal to 0 and solve. So that would be 24 minus 1.6t, set that equal to 0. We already did the work in part A to come up with the derivative function, which happened to be the velocity function. So set that equal to 0 and solve. Add the 1.6t to both sides. Divide both sides by 1.6. So the 24 divided by the 1.6 should give us the 15 that we determined just visually, right? So how long did it take to reach its highest point? It took 15 seconds. All right, now it's asking what is the highest point, right? Essentially, how high did the rock go? So it's asking for the position after 15 seconds. So it's asking what S of 15 is. All right. You can do that just by simple plugging and chugging. All right, just pop that right into the original function. S of 15 is going to be 24 times 15 minus 0.8 times 15 squared. We already know what the answer is going to be, so this is just showing the work. All right, so 24 times 15, you know. I could actually do it like this if I wanted to. F of x, and then pop in the f of 15. Get the 180 that way. I could tap on the graph because I took the time to make a nice window. We know the y value that corresponds to this is going to be 180. Or you could just physically type in the values that you see here. One way or the other, you should come up with 180 meters. All right. What was the rock's speed when it reached its highest point? Well, that was kind of how we developed the process to answer part B. All right. Its velocity was equal to 0. That's how we determined the moment in which it would be at its highest point. All right, so speed would be 0 meters per second. When did the rock reach half of its maximum height? All right, well, half of the maximum height would be 90 meters. So I would take my position function, S of t, and set it equal to 90, because I now have a position. I want the corresponding value of time. All right, so I'm looking for the value of t, bless you, the value of t that would give you a result of 90. You could solve that using whatever technique you like. You know, if you got to show all the steps and you see a decimal value, you might be thinking, all right, I'll use quadratic formula. You're probably not going to jump immediately to something like completing the square, but it is worth trying to factor. But personally, I like to use my resources. So even if I had to show all the steps, so I'll write it in the appropriate quadratic form. I would then pop it into Desmos, see what the answers would look like, what kind of answers I'd be up against, and then use that to determine what approach I should take. All right, so to do that, I would just let y equal 90, see where the intersections are. Those don't look like very clean intersections. I mean, it's possible that there are some reasonable decimal values, but, or I'm sorry, fractions that lead to these decimal values. Maybe it's just, cleaner than it appears, but I'm guessing that this is probably a quadratic formula situation. All right, so you remember the good old x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, this time it's t equals, but it's the same idea. So t equals negative b plus or minus the square root of b squared minus 4 times a times c. I never make my radical long enough. All over 2a. It's really the radical that's the troublemaker. If that ends up being something reasonably, I'll say reasonably irrational, something that could be simplified kind of nicely, then we're going to be in pretty good shape. If it's a nightmare, then that just makes things all the more tricky. Two negatives make a positive, so plus 4 times 0.8 times 90. So 864 under the radical, that's fun. All right, yeah.
Shouldn't it be negative 0.8?
Negative point. Oh, on the bottom. Thank you. Indeed.
And in the radical.
And in the radical. Jumping Jiminy. Thank you. So I got to fix this. 288. All right, that's nicer. Bless you. Yeah, so 288 is 144 times 2, so that's nice. Or nicer, anyway. So negative 24 plus or minus, that would be 12 radical 2. Over negative 1.6. Make that look a little bit better. So let me just adjust. So this should have been negative the whole time. Because I brought, yeah. Just cleaning up my notes. Yeah. Looking a little bit better now. All right, so then I want to try to clean this up a little bit more, but it's not really going to get much better because we already know the answers are going to be hideous. So it's just a question of, all right, well, let's see if we can make it somewhat less hideous than what we see in front of us. I'm going to slide that decimal over, just multiply everything by 10, and then we'll simplify from there. All right, all these coefficients are divisible definitely by 4, also by 8. Are they? They may even be divisible by. I didn't even think of that. Are they divisible by 16? Not the 120 though, right?
Not 120.
Yeah. So we can get an 8 out of it. So negative 30 plus or minus 15 radical 2 over a negative 2. And then I could just negate everything so I don't have that negative on the bottom. So 30 plus or minus 15 radical 2 over 2. So that's what t would be in simplest radical form. So it's really just a question of whether these roots or these values would equate to these values. So we're going to find that out in a sec. All right, 4.39 and change. That was one of them. So we're good there. Oops, that should be at 90. The other one should be somewhere in the neighborhood of 25. So a little duplicate, make the minus into a plus. Oops, make the minus into a plus. 25 and change, 25.6-ish. So we got there. Now, if they only want the decimal values, which usually ends up being the case, but you never really know, whoever they are. Yeah, just tap on some values on Desmos and call it a day. But you know, if we want the exact values, or as exact as you can get, then this would be the approach to take.
How would you know which it's asking for?
Well, in this case, they didn't really say, so I just figured let's find both. And on a quiz, you would just say, "Oh, round to the nearest tenth." All right, sounds good. Yeah.
Does it matter like whether it's plus or minus? Like,
In this case, it doesn't, because both of them would give solutions.
okay.
But if one of them gave you like a negative time as a result, then you would dismiss that. All right. So then the last one asks, how long was the rock aloft? So what we would need are any instances in which the position is equal to 0. So we go back to the original function. It's an easier computation though, which is nice. And we set that equal to 0. Now, for this one, and it only kind of works out because the object was launched from ground level. But when that happens, and you have full symmetry, once you've identified the maximum, so you know how long it takes to reach its maximum, if it's symmetrical, then you know that it would take that same amount of time to go from the maximum back down to the ground level. But there are plenty of instances that we've seen where it's launched from some other height. All right. So let's say it's already starting off 20 meters off the ground. If that's the case, then the amount of time it takes to get from that 20-meter mark to the maximum height would be the same amount of time it would take to get from that maximum height back to the 20-meter mark. It wouldn't account for the distance going from the 20-meter mark back down to 0. All right. This would only work as kind of a shortcut because it's starting off on ground level and ending up on ground level. All right. So for this one, we could say 30 seconds because it took 15 seconds to get to its maximum height. 15 times 2 is 30. All right. But we have to make the assumption that that's not always going to be the way it plays out. Like if it has some initial height, for example, in this case, if I said plus 20, that little initial height here screws everything up. All right. Because now it's not purely symmetrical, and we can't just double the time to get to the maximum height and call that the total travel time. All right. So set it equal to 0. Now, fortunately, this is just a clean GCF situation. Factor out a t. You could also factor out a 0.8, but it's not really necessary. So 24 minus 0.8 t equal to 0. Set each factor equal to 0 and solve. T equals 0. We already knew that. 24 minus 0.8 t equal to 0. So 24 is equal to 0.8 t. Divide both sides by 0.8, and you get t equals 30. All right. Now again, there's certain conditions that are at work here, or constraints, that allow this number to be the total amount of time that the object is in the air. But it's really the difference between these two numbers. So we have the initial and the final value for t, or at least the initial relevant value of t and the final relevant value of t. The difference between those two are what indicate how long the object's been in the air. All right? Because it is possible that you could have had something that was shifted over to the right a little bit. All right, so let me see if I can come up with that function real quick. Let's say it was g of x equals negative 0.8. The vertex was x minus, so x minus 15 squared plus 30. No, plus 180 is what it was, right? I don't know where I came up with 30. All right, so this is another way of writing this function. But let's say it was shifted over, just a little bit. Same characteristics, same maximum height, same time it would take to get to the maximum height. But if I just found the roots here, I'd find the roots at 35 and 5. All right, this would be an instance where somebody started the clock, 5 seconds elapsed, then they launched the object. All right, so you think about like lighting some fireworks or something. You light the fuse, 5 seconds later it launches. All right, so it's between the 5 and 35 seconds here that the object is aloft. It's not 35 seconds. It's not that it's in the air for 35 seconds. Just because it landed 35 seconds later didn't mean it was in the air for 35 seconds. All right. So that's just a quick example. But in this case, it would be 30 seconds minus 0 seconds. So this is the final. This is the initial. So the difference would be 30 seconds. And that's the travel time. And that's really it.